The man who doesn't need an introduction gets a quick introduction. Together with Eugene, I had the honor of founding Data Science Sydney in 2014. Again, time flies. He is the CEO of Prescient, a data science training company operating here in Australia and overseas. He's chief data scientist of Alpha Zeta, a global analytics consultancy, founding partner at Advantage Data, who are active here in Australia doing analytics and data commercialization. That is a difficult word. And he's a principal data science advisor to a growing number of technology startups covering the fields of banking, entertainment, medicine, sport and insurance. Eugene, I'm very glad you still could find time to come here today. And now the stage is all yours to tell us more about quantum computing and quantum machine learning. Thank you for being here.
Thanks, buddy. And what a odd experience it is to see Fabian do this, which I'm sure he has done many times in the last 4 years, but I'm usually the one when I'm here, so he does this really well. I should just let him do this. Good job. Welcome, one and all. This is packed. I think this is it genuinely standing room only, or is everyone being like trendy standing desk people? I guess a mix. Anyway, well, welcome one and all. Very hard act to follow with Sachin, but the bar has been raised. It was a great presentation, wasn't it? Give Sachin another hand, folks. So now I show my complete ineptitude with Google Docs, and an opportune time to help to acknowledge the person who's really helped so much in putting these slides together. Where are you, Sarah? And Sarah, I think, has many gifts, skills, knowledge, you know, background in pure maths and a PhD in physics, least among them. I mean, that's what helps her, you know, get through this quantum computing stuff. But what makes her unique is that when the rest of us say cool or awesome, she says hectic.
That's true.
This is going to be a really hectic talk, Eugene. I think I've got this. I think if I go to present from beginning, that worked. Okay. And that was it. That was all I was going to show you. That was the demo. Thank you. Everyone can now go home. So I thought I'd start with the shameless self-promotion, because that's where I usually start, isn't it? It's important to note that Prescient does have a quantum computing course, strictly speaking an introduction to quantum computing course, running, well, in mid-March. That's pretty soon. And then again, you can do it twice. You can do it in Sydney and Melbourne, right? Because you want to do my courses twice. And everyone wants to go to Melbourne, do they? I don't know. Yeah, so that's the course. I am, as Fabian said, involved in a growing number of companies. You should look up Alpha Zeta and Advantage Data if you want to talk to me about any of those things. With Alpha Zeta in particular, there are fantastic opportunities for independent data scientists, and I'll take this opportunity to make another announcement, which is, you've heard about the visualization stream of Data Science Sydney, you've heard about the new management stream of Data Science Sydney, you heard from me in both of them, let's face it. It won't be me presenting further on, but now's a good time to reintroduce one of the leading lights of data science in Sydney, Mr. Ian Hansel. Stand up. And Ian is leading up the new career and practice stream of Data Science Sydney, and we are going to be running an event soonish. Since these events fill up in 2 or 3 days, giving you a week's notice is not so bad, but we've got premises, and what I'll be presenting on, yes, me again, will be the questions you really need to ask prospective employers so that your data science job is going to be a dream and not a nightmare. Ask me about Alpha Zeta if you want to become a freelance data scientist, and I'll be more on that in future. Ask me about Prescient if you want to find out about data science courses, and ask me about Advantage Data if you want to give me enormous amounts of money for consulting. So, what are we talking about today? Oh yeah, from quantum computing to quantum machine learning. Is that right, Sarah? Is that what I'm Yeah, might as well. All right. Yeah, let's do that. Let's do that. You believed me. Okay, so, yep, big talk. And are we going to cover this entire field in 40 minutes? Heck no. But it's going to take at least 40 minutes to even give you the introduction to the introduction, which is what this is. And therefore, there won't be the luxurious time for questions, which Sachin handles so well. Again, he's a hard act to follow. I guess I'm intimidated by you folks. But look, in the informal drink section, etc., I can certainly answer questions. I'm sure you'll have some. So let's start at the beginning. What's machine learning? Machine learning is learning from data. Kind of a topical slide, actually. What do we do with machine learning? Well, a lot of us use machine learning to do customer analytics, right? Mostly customer targeting for retention, campaign response, fraud. What else? Credit scoring, insurance claims, likelihood of wearing purple, I don't know, lots of stuff. And of course, recommender systems, but that's so 2014. And the most important application of all, as you saw, is turning horses into zebras. That is certainly a key discipline of data science, and horse into zebrology is a growing field of research in its own right. And of course, there's the relatively minor field of medicine and computer-assisted diagnosis, which is benefiting greatly from zebrology. But this talk isn't about all that stuff. Well, it is in passing. It's about quantum machine learning, and what the heck is it? And why do it? In fact, as you'll discover, why do it is an interesting question, because there's also a question of, can we do it? Is it something that's doable? What does it even mean? So, quantum machine learning, it can be divided, I guess, into two, I would say possibly three things. I always do this. I look at slides and I go, yeah, three things, maybe two things, maybe three, and it's a fuzzy distinction, but here we go. Whatever the heck quantum machine learning is, and whatever the heck quantum computing is, and that's a big what the heck, which we will get into, it's, first of all, if you want to not think about it too much, if you want to think about it as a thing in the world, as a black box, as something you don't have to think about, one of the things it promises to be is it promises to do for lots of things what the GPU did for deep learning. It just promises to make things ridiculously, unbelievably fast. I just saw that guy's t-shirt, and it's an awesome t-shirt. It says, Bayes rule, exclamation mark. I like the t-shirt. So, that was an important point. You distracted me. Stop it with the t-shirts. So this is the important point. The simplest and most sort of abstracted out, perhaps wantonly dismissive view of quantum computing is that quantum computing is just a way of making computing faster. Now, that faster is sort of faster in capital bold letters raised to 25 point and flashing red. You've got that image in your minds now, don't you? It is unbelievably fast. If it does what it's supposed to, and we'll discuss about why it's an if, but it's speed up way beyond anything that our current hardware speed-ups, be they FPGAs or GPUs or overclocked whatever machines you've got in your fridge, or giant prem or web clusters. I learnt the word prem recently. I feel like a professional. So quantum computing promises to be much faster than all of these things, and I guess its first application in machine learning is to do what GPUs do, which is to take the low-level mathematical computation steps of some of these algorithms and massively speed them up. So things like matrix operations. There's a few other things that quantum algorithms can do reasonably well. We'll mention some of them later, things like Fourier transforms. So what they can speed up, it looks like they can speed up very well indeed. But the other thing they can do is create new quantum computing algorithms, new machine learning algorithms in their own right. And there's a kind of thing in the middle where algorithms that have been around for ages but weren't viable suddenly become viable and very powerful. By the way, a very similar thing happened with much of deep learning. A lot of deep learning technology isn't really that new, but its application is new because the computational power is there. Convolutional nets have been around since at least the early 90s. I'm pretty sure they were there probably in the late 80s even. I learnt about them in 1991. But they weren't viable then, and they are viable now. But back to quantum computing, all of that is point 2 here. See, point 2 is everything I've just described in one tiny little bundle, which is where we use whatever it is that quantum computing does to solve the sort of problems we're solving now. But then there's another whole class of things of interest more to physicists, which is that quantum computing is a uniquely placed set of methods for looking at quantum systems, for actually modeling the behavior of quantum systems. Probably less to say about that in this talk, probably less interesting to you, but you should know that that's an area in its own right. So yeah, we'll be focusing on how do we extend or replace the machine learning we're doing now with quantum computation. Because, well, we are in many ways approaching the limits of classical computational models. We've got good at scaling things up just by having more cores or by having more nodes. We've gotten good at speeding things up by having dedicated hardware like GPUs. That's all great. But if we want an absolute step change in speed, that is what quantum computing at least promises. So here we have examples of papers, one on using machine learning to analyze quantum systems, and there's quite a few papers on that for physicists to do their physics stuff, and one on using quantum computing to do general machine learning or general optimization or general quant stuff, which it looks like they may well do very well. You hear me keep talking about all of this as being future tense. I'll get onto what is possible now and what looks like being possible later and what the challenges are shortly. So to give you an overview of the talk, with a picture of what look like multiple quantum states of a particle. I guess is that an atom? I don't know, Sarah. When I saw it first, I thought they were like relativistic, what are they called, light cones, except you can't have multiple light cones like that. So we'll talk about what is the status of quantum computing today, because underlying quantum machine learning is the more fundamental and very non-trivial field of quantum computing. And we'll talk about why it's different, why it's special. And they're special because they're weird, they're special because they're powerful, and they're special because they're tricky. I'll then talk about specifically how machine learning impacts quantum computing, or vice versa. And finally, these slides will have some material on how to actually use an actual quantum computer. I'm pretty sure we won't get to those steps, but they're there in the slides, and I'm almost certainly going to make the slides available to you in the current form. So, what's the status of quantum computing today? I think it's fair to say that quantum computing is where classical computing was in the 50s, maybe even the 40s, in the sense that if you want to be working with a computer in the early 50s, in the 40s, you'd be talking about working directly with individual bits, you'd be working directly with individual gates, and the analogies of bits and gates, which I'll discuss with you, which require a lot of discussion, are pretty much where we're at with quantum computers. So the bad news is very, very much in their baby stages. More of a proof of concept these days than a viable commercial application, which is not to say that there isn't at least one very large organization that's already announced commercial partnerships and commercial availability of their quantum computers. So that proof of concept has escaped from the lab. There are challenges. There are reasons why quantum computing is still in its infancy, and I'll mention them now. Maybe I'll go into a bit more detail later. One is scale. So the equivalent of a bit in a quantum computer is called a qubit, and it turns out that the more qubits you have, the better. And indeed, the power of quantum computers grows exponentially with the number of qubits. So your existing computer, this laptop I've got here, has, what, billions of bits in it. In fact, probably tens or hundreds of billions of bits, close to thousands of billions of bits, right? Trillions. But a quantum computer, well, the ones that are around now have, the most powerful ones I know of that are universal quantum computers have something like 50. But it turns out that if you can get a quantum computer working with 50 qubits, you should theoretically be able to solve real-world problems in blindingly fast ways that no classical computer can ever match. And if you double that number of qubits again, you start getting absolute miracles. So getting that scale is hard. It's an engineering challenge, it's a physics challenge. But that scale, we're talking about tens or hundreds of qubits, not billions. Why is that the case? Because for 100 real qubits, you effectively get a heck of a lot more virtual ones, and we'll talk about that shortly. There is something called quantum noise. These things are not terribly stable, so being able to do very complex computations with them now is challenging. So another challenge is to let us build pipelines of functions, of transformations, of gates, the way regular computers do. That's still a challenge. And even getting data into quantum computers is a bit of a challenge now. So for a lot of tasks, the computation itself is blindingly fast, but that's if you discount how long it took to get the data into the quantum computer. Challenges do exist, and they're being addressed. The good news is that quantum computers actually exist, and until about 5 years ago, you'd be reading articles where people would say, we don't think there'll ever be quantum computers, it's all hype, we never seem to see them. Well, suddenly we saw them. Suddenly we saw them, they exist. In fact, they exist on the cloud, and you can actually program them. IBM's Q Experience, which makes a 5-qubit computer available, you can actually do their tutorials. You can run what are called quantum simulators, and you can actually run code on the actual quantum computer itself. It'll be scheduled to run. You won't get the results straight away, but if you want to go and tell your friends how you've actually run code on a quantum computer, well, you actually can. And last time I did it, it was free. Hopefully it's still free for you to try. They require controlled environments. See those vats? Now, those vats used to be what the US government, the NSA, used to store the aliens that crash landed in Roswell. But yeah, the aliens have been evicted. They're not very good at paying rent, and they've been replaced with cryogenic chambers. The truth is that quantum computers are kept in these vats where they're kept extremely cold, absolute zero, near the temperature of space, because you need these extremely low temperatures to maintain the stability of these things called qubits. Qubits are incredibly fragile. So they require these controlled environments, and there are a number of organizations that have either built quantum computers or are in the process of building them. So the most notable one, the one that's had quantum computers visibly and commercially available for the longest time, is D-Wave. So D-Wave has actually been selling quantum computers for years now. And their quantum computer is different. Theirs is what's called a specialized, it's a specialized form of quantum computer. It's a quantum annealing or adiabatic quantum computer. So it's sort of a one-trick pony. It's like a specialized bit of hardware that does one thing and does it well. And the thing it does is a form of optimization called quantum annealing. And those of you who know what simulated annealing is, well, this is like a quantum analogy. But IBM has certainly made available what might be called a universal quantum computer, and we'll talk more about that distinction. Microsoft hasn't, to my knowledge, made any hardware available yet, but they're working on their own version of hardware called a topological quantum computer. Microsoft has, however, made a quantum language available called Q#. There are a number of quantum languages for doing what's called quantum programming. More on that. So we can use quantum computers. Sarah's probably shaking her head and saying, he should have said that in the later slide. What's he doing? So as you can see, Sarah's done some great work with color coding the slide components. So she'll tell you which bits which bits are IBM, and which bits are Rigetti. So there's a company called Rigetti that's not one of the big names, but they're doing some amazing things with universal quantum computing as well, and they do have quantum hardware available, and indeed they have claimed to be the first company to run what they call a machine learning algorithm on a universal quantum computer, which I believe was cluster analysis on the IRIS dataset. People who did my R course know all about the IRIS dataset. Not a bad dataset for a clustering problem, by the way. And they have their own language called Quill. So yet another quantum programming language with of course, a Python wrapper called PyQuil. IBM's own language is called QASM. It's their open quantum assembly language. And I think now's the time when we dive deep into what the heck we mean by quantum computing. And quantum computing means using the power of quantum mechanics, taking advantage of certain characteristics of quantum mechanics, and this is where things get weird. Quantum mechanics is weird in a very fundamental way. Weird in the sense of it completely and utterly evades human intuition. Philosophers have racked their brains for the better part of, almost 100 years now, trying to find ways to explain what the heck it is that happens in quantum systems, and they can't. All we know is that the mathematics works, the experiments bear out that the mathematics works, and every time we try to find a common sense gotcha, like Einstein came up with a common sense gotcha for quantum mechanics and said, look, if quantum mechanics does what it's supposed to do, then this thing, and I'll get to what that thing is later, this thing couldn't possibly work because it's nuts. Well, the experiment was done well after Einstein's passing, unfortunately, and guess what? Einstein was wrong, and the universe really is that weird. It turns out that that weirdness is something we can actually harness. So quantum computing harnesses the weirdness to be extremely powerful. I should also mention one more thing, that quantum mechanics is tricky. So I will talk about the conceptual tools required to master, or even, well, to access quantum computing. And as you'll see, the analogues to regular computing that quantum computing requires are, rather extensive. So first of all, I want to talk about the power of quantum computing. See, normal computers have bits, right? And bits can be on or off. Simple. Well, later we're going to get, I'll give you, there's our friend Schrodinger's cat. I'm going to talk about Schrodinger's cat shortly. Because if we're talking about Schrodinger's cat, we're talking about this weird thing that happens at the quantum level where things can be in multiple states at the same time. And they're not like in a state in the middle, they're just in both states at the same time. What does that mean? How does that even make sense? Well, every time I talk to my physics friends about that, they say, well, just because it evades your classical human intuition doesn't mean you're right and the quantum world is wrong. It just means there's something wrong with our intuition. So I can't tell you how to understand it, other than all you can do is accept it and realize that the power of realizing that these things being on and off simultaneously is in some, it's real. It's more real than thinking that it's one or the other. And what does that mean in practice? That means in practice that if you do a computation on one real bit in the real world on a real computer, well, on a register of bits, let's take a register of 8 bits. You've got 8 bits and you do some sort of computation on those 8 bits. It's a function, right? It takes those 8 bits, plugs it into some sort of machine, a whole lot of logic gates, and out comes some kind of result. We get a result, right? One set of bits, result. Use another set of bits, we get another result. But with qubits, we can actually stack 8 qubits. With 8 qubits, each of those qubits is simultaneously on and off. It can be simultaneously on and off. In fact, there are many different ways for it to be simultaneously on and off. More on that later. And there's a way to not just think about each qubit being simultaneously on and off, but more importantly, taking that whole register of 8 qubits and saying there are actually 2 to the 8 different possible combinations of on and off here. And one way to think about what quantum computing does, and this is pretty crazy, is to talk about one more thing, which is that you go from this weird world of things existing and not existing at the same time to the world we know and love where everything does exist when you do this thing called measurement. See, whenever we look at things, we listen to things, we're measuring all the time. So we don't notice this quantum reality because we're constantly doing what's called collapsing the wave function. We're constantly forcing the world to randomly take one of the values, one of the possible values that occurs. But until we measure the world, it's in all of these states. So quantum computing does a very strange thing. Well, one interpretation of quantum computing is that there are all these possibilities. And when we make a measurement, what we do is we just, a version of ourselves finds ourselves in one of the possible universes that are a consequence. The collapse of the wave function is really, it's ending up in one of several parallel universes. But there's another you to whom the other thing happened. What does this mean for quantum computing? This is relevant for quantum computing because we can look at quantum computing as a way of harnessing parallel computation across multiple universes. We're actually stealing computation from parallel universes and letting it leak into the universe we find ourselves in. Now that sounds completely nuts, doesn't it? But that is one of the valid interpretations of quantum mechanics. So quantum mechanics says that with 8 qubits, we have 2 to the 8 possible parallel computations happening. With 100 qubits, we can have 2 to the 100 computations, and you can imagine what would happen with 1,000 qubits. So all these computations happen in parallel because the output of each of those computations also exist in these parallel worlds. Now, when you measure them, you're destroying all except for one. But quantum computing gives us a way of doing a kind of a map reduce. You map to parallel universes and you reduce in a way that it comes back, sends a message to the universe you actually end up in. And it's this massive parallelism which gives you the speed. Now, the goal of quantum computing is what's called quantum supremacy. It's to show undeniably that quantum computing can do stuff way, 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 way faster than any classical computer, and we haven't got there yet. Google promised to give us undeniable quantum supremacy last year. They're saying, give us a bit more time. D-Wave is still working on it. I'm going to get into the Schrodinger's cat issue just very quickly. Those of you who haven't heard about it, it's a rather macabre way of looking at this quantum superposition thing. You put a cat in a box, there's a radioisotope which, if it decays, releases a poison, which may or may not happen, and if it happens, the cat is dead. Is the cat dead or alive? Well, until you open the box, the cat is both. When you open the box, you measure it. You figure out what it is. So in a classical system, a bit is 1 or 0, like it's either 100% chance that it's a 1 and a 0% chance that it's a 0. In a quantum system, it can be 50% both. It can be 50% in the 1 state and 50% chance it can be in a 0 state. And in fact, it can be any combination whose norm adds up to 1, where the numbers themselves can be complex numbers. Hands up here who knows what a complex number is. That's good, because one of the prereqs of getting anywhere with quantum computing is knowing what the heck a complex number is. Now, a beautiful demonstration of superposition is Schrodinger's cat, and a beautiful demonstration of the other bit of quantum weirdness is entanglement. And it's when groups of particles have this weird, spooky action at a distance relationship between them. And we need entanglement to put together these quantum registers of qubits. One way to get entanglement is to get a ball of blue string and tie it around a kitten. No, that probably doesn't help, but it's very cute. Good one, Sarah. But Einstein was the one who said, well, you know, you just can't do entanglement, and there's a slide here which talks about how it works. Basically, entanglement is insane. It means that you can fire particles to 2 different planets. 2 entangled particles can be fired at 2 different planets that are like, I don't know, a light year away from each other. And the moment you measure one particle's property, be it spin or whatever, the quantum property that's entangled, that will give you, with much higher probability than random, that there will be the same measurement on the other particle. They have this weird relationship that maintains over any distance and resolves instantaneously. Einstein's biggest argument against quantum mechanics was a thought experiment that said that this would happen, and it can't because it's preposterous. But Bell's experiment, which was carried out, in the 60s, I think, proved that it is in fact entirely the case. So combining superposition, which is the Schrodinger's cat thing, and entanglement, which is this particles never separate, we get quantum computing. And how does it compare to quantum computing? Well, we have these, like you can have a NOT gate in a regular computer. It just sort of inverts a 1 to a 0. A quantum NOT gate does much the same thing. It also inverts the 1 to a 0 and a 0 to a 1, where they just swap coefficients. And then you measure it. But then when you measure it, well, it's only ever going to be a 0 or a 1, and this is probabilistic. Why is the measurement probabilistic? Just because it is. It makes no sense. There is no coherent, nice narrative for why. It just works. Unfortunately, quantum mechanics is like your mother when you're 5, and you say, but why? And she says, because I said so. That's what quantum mechanics is like. And entanglement, the spooky action distance, is how we get that magic parallelization bits. So a bit of comparison of classical versus quantum computers. Classical computers, well, bits go into the computer, they come out as bits. In quantum computers, they start out as qubits, and then when you measure, you read out to bits. Now, this is the scariest thing. If you're doing programming, standard programming, you will instinctively have a mind for Boolean operations. You can't do programming and not be able to think in Boolean logic. Agreed? It's just impossible. You got to have an instinct for it. Guess what the equivalent is with quantum computing, and therefore quantum machine learning? Complex unitary linear algebra. In fact, complex unitary matrix algebra. Tensor algebra. So you need to have an instinct for complex valued matrices, the way you have an instinct for simple Boolean logic. In other words, you can't fake this. You can't just go, hey, I've downloaded the Python package for quantum computing, look at me. It doesn't quite work that way. There's a lot more to learn here. The whole idea of something being in the state A or B is replaced by all this weird superposition and entanglement business. The fact that you can read a state reliably is replaced by this probabilistic thing that destroys information by collapsing it from multiple universes. There are universal gates in both cases, but they're different universal gates. And all quantum operations, except for measurement, have to be reversible. Now, this actually is a very interesting restriction. And the other weird thing, it sounds completely nuts, but it's true, you can't copy quantum states. Now, copying is such a trivial part of regular programming, you just don't even think about it, right? But you cannot copy a quantum state. There's something unique and uncopyable, unclonable about a quantum state. Just like there are gates in quantum operations, the NOT gate, the AND gate, the OR gate, there are similar quantum versions of that, the conditional gate, the conditional NOT gate, the C-NOT gate. There is AND and OR, actually conditional AND, conditional OR, I believe. But there's also weird gates to do stuff that has no analogy in the classical case, like the Hadamard matrix, which takes a 0 or a 1 and turns it into a superposition, or different rotation and phase shifts, which indeed are what unitary matrices are more generally. So, look, the quantum computing requires some serious maths. It requires you to know complex numbers, which is that first bit. It requires you to know matrices and an abstract algebra. It requires you to know a bit of calculus, and that beautiful, colorful thing there is a tensor. So everyone's heard of TensorFlow, but if you've ever wondered what the heck an actual tensor is, a tensor, for those of you who are scared of matrices, makes a matrix look like a baby. So if a matrix is two-dimensional, a tensor is 3 or more dimensions, and that's what makes TensorFlow interesting. But you need to be able to actually think in them. Yeah, it's like that. So what sort of quantum computers out there? D-Wave does quantum annealing, as I mentioned. D-Wave has been sold to Google, to NASA, to Lockheed, I believe, to a number of US Navy, I think, to a number of outfits. D-Wave is specialized. D-Wave is the oldest. D-Wave can do some interesting things. The universal quantum computers are much more interesting. They're an analogy to the computers we have on our desks. They're the computers that can do just about anything. They're newer, they're less stable, they're harder to scale, but they're the ones just about everyone's working on. They're the most interesting things. And of course, Australia is a big player in this with the first Australian quantum computing company, Silicon Quantum Computing, was launched with a high-profile board and investment boost. There's the article there. And, you know, some big money's gone into it. UNSW, this place, the Combank of Australia, Telstra, our federal government, the New South Wales government, and here are the dollars that they're all throwing around. So for those of you who don't look at life in terms of truth, but look at life in terms of social proof and dollars, you know who you are, and you should be ashamed. This is the social proof and the dollar proof. So Commonwealth Bank has a revolutionary quantum computer simulator. Does anyone here from Combank actually work with the quantum computing? I want to talk to you. I want to talk to you. Microsoft and the University of Sydney forge a quantum partnership. What are you doing about that, IBM? And look, about $100 million invested by the Australian government and industry over the past decade in the related areas. Now, how does this all relate to machine learning? Well, quite simply, there are two approaches. One is to chuck in little bridges of quantum computing to speed up existing algorithms. One is to come up with whole new algorithms, which also includes the addition of the sort of reawakening, the reanimation of unviable algorithms in the past. And two ways to improve it. One is to just squeeze more data in because of this superposition business, not terribly interesting, and one is make things much faster because of this massive parallelization. So here's a whole bunch of papers on quantum enhancements for machine learning, and they've come with references and so forth, so you can chase them to your heart's content. So there's a survey of the field, specific things like some things quantum computing seems to be better for some things than others. There's deep learning, support vector machines, Bayesian inference, quantum principal components. Haven't seen anything on trees. I don't think quantum computing is really good for trees, but it does amazing things with neural nets. A few other papers. Quantum annealing, we've mentioned quantum annealing. These are, I believe, experimental results, whereas, so these were theoretical, but here are some experimental results. Combinatorial optimization with the D-Wave computer. Is D-Wave really better? There's ongoing debate, and the debate happens at two levels. A, is it better? B, what does better even mean? How do we benchmark these? People are still debating that. So, you know, papers on, well, how the heck do we define the benchmarks in the first place? Universal computers are so new, we don't even know how to benchmark them. IBM comes out with their volume benchmark out of the blue. Personally, I'm interested in the speed. I think it's all about the speed. But hey, IBM's bigger than me, so I won't argue with them. More papers on quantum speed up. Now, quantum Boltzmann machines I am fascinated by, because of all of the things that I've seen in the quantum field. It's one thing to say, yeah, we can do stuff faster. Yeah, that's interesting, fine. But there's one kind of machine learning that's been around since the 80s, but hasn't been viable. And it's called, well, the Hopfield network, and a refined extension of it called the Boltzmann machine. And it's like the recurrent neural net from hell. It's a fully connected neural net that learns using kind of an unsupervised approach. But to call it supervised or unsupervised is to kind of miss the point. It's bigger than that domain. It may be able to do things that none of the existing methods do. And with quantum computing, we can actually find out. So we're talking about a fully connected method that can do what's called content addressable memory. So it can actually remember the way we remember. We don't remember by, you know, a numerical address to a box. We remember by going, hey, that thing reminds us of that. We remember being reminded. We remember by being shown a piece of something or something associated with something and bringing the rest of it back. Well, this is what Hopfield nets and Boltzmann nets can do, and with quantum computing they can do it at scale that makes them more than toys. And further work on quantum AI. So we're talking about learning agents in quantum environments and quantum agents. Quantum pattern recognition, multi-neuron interactions. There's that quantum Hopfield neural network and the quantum Boltzmann machine. This, I think, is the AI promise from from quantum computing. So where are we at? Where is Skynet at? Well, we can already build baby quantum computers. Yes, they're noisy, yes, they're small, but they're there. Have we achieved quantum supremacy? People are arguing. You know, some people are saying, yes, we already have. Jury's out. Have we built stable quantum computers at scale? Heck no. That's a big challenge. So the stable bit is a challenge, the at scale bit is a challenge. And can we combine machine learning with quantum computing? Well, like, as I said, until about 2 months ago, the answer was not yet. But in terms of universal quantum computing, it's been done. It's been done with a clustering algorithm, sure, but it's a start. And that's this year. You're going to see results come in every few weeks or every month. This year is a very interesting year for quantum computing results. So here is a page with further reading. I draw your attention specifically to, in the foundational area, at the bottom there, Quantum Computation and Quantum Information by Michael Nielsen and Isaac Chung. So quantum computation, quantum information is a mouthful. Lots of people call it Nielsen and Chung. People in the know call it Mike and Ike. It's a really hard read, but it's worth it. Other than that, there are a whole lot of other things you can read to get into the field. The YouTube series by Michael Nielsen is great. There's an online course. The MIT course is great. The IBM Q Experience website is great. And more importantly, Prescient's got a course, which we're running 13th to 14th of March, and this will be the first one. This is the introductory one, but following will be a proper quantum programming course and indeed a quantum machine learning course. Fabian probably wants me to stop and possibly to kill me at this point. Where are we at, Fabian? Where's Fabian?
Yeah, you're totally over time.
Okay, so questions will have to go to where I'm going to get wine. Thank you all very much.
Yeah, that was my impression as well. Quantum computing is best discussed over wine.
That's your one.
Cheers to that. So, last item on our schedule today. Are there any announcements? Jobs, opportunities, great things to share?
Well, let's start with Greg.
Where's Greg?
Always start with Greg.
Well, thank you for tonight. First of all, just want to say thank you to Troy and Kate. If you haven't had a look at the Data Science Sydney YouTube, there's about 20 odd different past presentations, all very valuable to look at. But that's, yeah, please go and have a look at that. Greg Pearl from N-World Recruitment. I purely focus, a lot of you know me anyway, I've been here as part of furniture, but focus purely on data science recruitment. Please come and have a chat to me. I'm doing a lot of work around the artificial intelligence space, working with Stone and Chalk and Fishburners in the startup community. If you want to talk about that and get into that, please come and have a chat. If anyone's looking to recruit any good data science individuals, there are a number of really good individuals around. Please come and have a chat to me as well. But thank you. Yes.
Okay, I'm Perry from the Commonwealth Bank. I'm a data scientist here in our data science team. I have three things. Two very quickly about the meetup. Firstly, please make sure that you put your visitors' passes back in the box on the way out so that I don't get necked. Two, please update your profile on Meetup so that you have both your first name and your last name so that I don't get necked. Because I get in trouble when I give them a guest list that doesn't have your first name and last name. It's not that I don't want to allow you to be anonymous, it's that I'm not allowed to allow you to be anonymous. And thirdly is that we're hiring. So if you want to work at one of the biggest companies in the world, really, I suppose, we're the 11th biggest bank in the world, I found out recently. If you want to do data science at scale, if you want to do deep learning at scale, if you want to work on quantum computing, we are hiring. We're interested in people all the way through the spectrum, from researchers that have just come out of academia, all the way through to data science practitioners, people who are really good practically on the ground working with stakeholders. Come see me, find me on LinkedIn, find Kevin, find Manish, find anyone from Seagate on LinkedIn and we'll point you in the right direction. Thank you.
Hello, my name is Kate Brown and I'm also from CBA. We don't work in the A&I world, but we work in a different part. We're currently looking for a data engineer to join our team on a permanent basis. So if anyone's interested, we're building a really awesome tool that's serving the whole bank and allowing us to build insights into the maturity level of their CI/CD pipeline. So do come and have a chat afterwards if anyone's interested. Thank you.
Wonderful, thank you very much. Any other announcements? think of that. I think the only thing we haven't mentioned that yet